Welcome back. In this session, we discuss the limit and continuity of functions of two variables. In real world situations, most of the measurable quantities depend on more than one factor. The volume V of a circular cylinder of radius r and height h is given by V equals pi r square h. If r and h vary, we can say that volume V is a function of two variables r and h. The interest accrued for a principal amount P at a rate of 5% per year compounded annually for a period of t years is a function of P and t. The area of a rectangular shape is a function of its length and breadth. This indicates that the function of several variables appear more often in many applications in science and engineering. This section will extend the idea of limit of functions of two variables. A function of single variable x is denoted by f of x. A function f of two variables x and y is a rule that assigns to each ordered pair x y in a given set D called the domain a unique value of f. Z equal to f of x y is a function of two variables. It has independent variables x and y and the dependent variable z. Let us consider a function z equal to f of x y of real variables x and y defined by f of x y equal to x plus 2y plus 3. If we specify the values x equal to 3 and y equal to 2, then we have a single value z equal to 10. In this case, we write f of 3 2 equal to 10. So, we can plot a point 3 2 10 in space as in figure A. The graph of function z equal to f of x y consists of all points of the form x y z, where x y is in the domain of f. Since the domain is a set of ordered pairs x y, we may consider the domain to be a part of x y plane. So, the graph of z equal to f of x y can be interpreted as a surface in 3 dimensions. Now, the concept of limits in 2 dimensions be extended to functions of two variables. In what follows, we consider real valued functions of two real variables. As in the case of functions of single variable, the informal definition of limit of functions of two variables can be stated as follows. A function f of x y has a limit L at a point a b if we can make the value of f approach L by taking x and y close to the point a b. Consider the example f of x y equal to x plus 2y plus 3. For the limit of this function to exist at 3 2, values of f of x y must get closer to 10 as points on the x y plane get closer and closer to 3 2. That is, f of x y approaches the value 10 as the neighboring points of 3 2 approach point 3 2. The neighboring points of a b in the x y plane can be described as the points within a square or circle centered at a b in the x y plane. Neighborhood of a point. Let delta be a small positive number. Square delta neighborhood. The set of all x y other than a b that satisfy the conditions absolute value of x minus a less than delta, absolute value of y minus b less than delta is said to form a square delta neighborhood of the point a b, circular delta neighborhood. The set of all x y other than a b that satisfy the condition absolute value of pair x y minus pair a b less than delta is said to form a circular delta neighborhood of the point a b. Here absolute value of x y minus a b is equals root of x minus a square plus y minus b square, which is the distance between the points x y and a b. Limit of a function of two variables. A real valued function f of x y of two real variables is said to have a limit L in R at the point a b if to every positive number epsilon there exists a positive number delta such that absolute value of f of x y minus L less than epsilon for all points x y other than a b, for which absolute value of x minus a less than delta and absolute value of y minus b less than delta, or absolute value of pair x y minus pair a b less than delta. If the limit exists, we write limit x y tends to a b f of x y equals L. Example. Let f of x y equal to x plus 2y. As x approaches 1 and y approaches 1, the function takes the value 3. Now, we prove using epsilon delta definition that the limit value of f of x y is 3. Here we have to show that for any number epsilon greater than 0, there corresponds a positive number delta satisfying the defining criterion. Absolute value of f of x y minus 3 is equal to absolute value of x plus 2y minus 3 equals absolute value of x minus 1 plus 2 times y minus 1, which is less than or equal to absolute value of x minus 1 plus 2 times absolute value of y minus 1. Let delta greater than 0 be an arbitrary number. Then 0 less than absolute value of x minus 1 less than delta and 0 less than absolute value of y minus 1 less than delta together imply that absolute value of f of x y minus 3 less than delta plus 2 delta, which equals 3 delta. For given small value epsilon greater than 0, choose delta equal to epsilon by 3. Then for any epsilon greater than 0, there corresponds a positive number delta equal to epsilon by 3 such that absolute value of f of x y minus 3 less than epsilon whenever 0 less than absolute value of x minus 1 less than delta and 0 less than absolute value of y minus 1 less than delta. This proves that limit x y tends to 1 1 f of x y equals 3. In the above example, we have taken the definition of limit based on square neighborhood of a point. Let us consider another example which uses the definition based on circular neighborhood. Example, let f of x y equal to 2x cube minus y cube by x square plus y square. We prove that limit x y tends to 0 0 f of x y equals 0. Here absolute value of 2x cube minus y cube by x square plus y square minus 0 equal to absolute value of 2x cube minus y cube by absolute value of x square plus y square. But absolute x less than or equal to x square plus y square whole raised to half and absolute y less than or equal to x square plus y square whole raised to half. Now absolute value of 2x cube minus y cube less than or equal to 2 absolute value of x cube plus absolute y cube less than or equal to 2 times x square plus y square whole raised to 3 by 2 plus x square plus y square whole raised to 3 by 2, which is equal to 3 times x square plus y square whole raised to 3 by 2. Thus absolute value of 2x cube minus y cube by x square plus y square minus 0 less than or equal to 3 times x square plus y square whole raised to 3 by 2 by x square plus y square, which is equal to 3 times x square plus y square whole raised to half. This quantity is less than epsilon whenever the distance x square plus y square whole raised to half between x y and 0 0 is less than epsilon by 3. So choose the positive number delta equal to epsilon by 3. Then for any epsilon greater than 0, there corresponds a positive number delta satisfying absolute value of 2x cube minus y cube by x square plus y square minus 0 less than 3 delta, which is equal to epsilon whenever 0 less than x square plus y square whole raised to half less than delta. Hence limit x y tends to 0 0 f of x y equal to 0. Remark: both the epsilon delta requirements in the definition of limit are equivalent. This assertion can be proved by showing that corresponding to a square neighborhood n of point AB, there exists a circular neighborhood B of AB which is contained in n and vice versa. Let n be a square delta neighborhood of AB. Consider the circular delta neighborhood B of AB and let xy belongs to B. Then absolute value of xy minus AB less than delta implies that x minus a square plus y minus b square less than delta. This shows that absolute value of x minus a less than delta and absolute value of y minus b less than delta, and hence the point xy belongs to n. Therefore B is contained in n. Conversely, let B be a circular delta neighborhood of point AB. Choose positive number delta 1 such that root 2 delta 1 less than delta and consider square delta 1 neighborhood n of AB. Let xy belongs to n. Then 0 less than absolute value of x minus a less than delta 1 and 0 less than absolute value of y minus b less than delta 1 implies that x minus a square plus y minus b square less than 2 delta 1 square less than delta square, and hence absolute value of xy minus ab less than delta. Therefore xy belongs to the circular delta neighborhood B and hence n is contained in B. Theorem: let f of xy be a real valued function of two real variables. If limit xy tends to ab f of xy exists, then the limit is unique. Proof: suppose that limit xy tends to ab f of xy equal to L and limit xy tends to ab f of xy equal to M. We prove that L equal to M. Assume that L not equal to M. choose positive number epsilon satisfying 0 less than epsilon less than half of absolute value of L minus m. Then for this epsilon greater than 0 corresponding to the limit value L, there exists number delta 1 greater than 0 such that absolute value of f of xy minus L less than epsilon whenever absolute value of xy minus ab less than delta 1. Similarly, corresponding to the value m, there exists delta 2 greater than 0 such that absolute value of f of xy minus m less than epsilon whenever absolute value of xy minus ab less than delta 2. Take delta equal to minimum of delta 1 comma delta 2. Then for all xy for which absolute value of xy minus ab less than delta, we have absolute value of f of xy minus L less than epsilon and absolute value of f of xy minus m less than epsilon. Thus, absolute value of L minus m equal to absolute value of L minus f of xy plus f of xy minus m less than or equal to absolute value of L minus f of xy plus absolute value of f of xy minus m less than epsilon plus epsilon. This shows that absolute value of L minus m less than 2 epsilon, which is a contradiction. Hence, L equal to m. This proves the theorem. Notice that the points xy in the neighborhood of AB can approach the point AB from any direction in an arbitrary manner. The definition of limit implies that the limit value must be the same along every approach path. This fact can be used to prove the non-existence of limit. Two-path test for non-existence of limit. If a function f of xy has different limit values along two different paths as xy approaches AB, then limit xy approaches AB f of xy does not exist. Example, let a real valued function f be defined by f of xy equal to y minus x by y plus x into 1 plus x by 1 plus y for real values x and y. We check the limit of f at the point 0, 0. Consider the straight line approach path to 0, 0. Corresponding the lines y equal to mx through 0, 0, we have f of xy equal to mx minus x by mx plus x into 1 plus x by 1 plus mx, which is equal to m minus 1 by m plus 1 into 1 plus x by 1 plus mx. Then limit xy tends to 0, 0, f of xy equal to m minus 1 by m plus 1 equal to L. The value L depends on the slope m. This shows that the limit value will not be the same for two different straight line approach paths to point 0, 0. So, the given function has no limit at 0, 0. Repeated limit. The definition of limit of two variable function implies that limit xy tends to AB x equal to a and limit xy tends to AB y equal to b. Let f of xy be defined in some neighborhood of AB. If we consider the limit of f of xy as a limit of function of one variable keeping other variable constant, we can see that limit y tends to b f of xy if it exists is a function of x and say phi of x. Let limit x tends to phi of x equal to lambda exist. Then we write limit x tends to a, limit y tends to b, f of xy equal to lambda. This is called the repeated limit of f as y tends to b, comma x tends to a. In the same manner, by changing the order, we can have the repeated limit of f as x tends to a, y tends to b. Suppose that limit xy tends to a b f of xy exists. Then the repeated limits limit x tends to a, limit y tends to b f of xy and limit y tends to b, limit x tends to a f of xy are equal. But the converse need not be true. We can use the property of repeated limit for establishing the non-existence of limit of f of xy. Let f of xy be defined in some neighborhood of AB and the repeated limits limit x tends to a, limit y tends to b f of xy and limit y tends to b, limit x tends to a f of xy exist. If limit x tends to a, limit y tends to b f of xy not equal to limit y tends to b, limit x tends to a f of xy, then limit xy tends to a b f of xy does not exist. Example, let f of xy equal to x minus y by x plus y be defined for positive real numbers x and y. We check the existence of limit xy tends to 0, 0 f of xy. First we find the repeated limits. Limit x tends to 0 of limit y tends to 0 x minus y by x plus y equal to limit x tends to 0 of x minus 0 by x plus 0, which is equal to limit x tends to 0 of 1 equals 1. Limit y tends to 0 of limit x tends to 0 x minus y by x plus y equal to limit y tends to 0 of minus y by y equals to minus 1. Thus, the repeated limits are different. So, the limit does not exist. Algebra of limits. The sum, difference, product and quotient of two functions f of x y and g of x y with the common domain D are defined as follows. F plus g of x y equal to f of x y plus g of x y. F minus g of x y equal to f of x y minus g of x y. F times g of x y equal to f of x y times g of x y. F by g of x y equal to f of x y by g of x y provided g of x y not equal to 0 for x y belongs to D. Theorem. If f, g be two functions defined on some neighborhood of a point a b such that limit f of x y and limit g of x y exist at a b, then limit f plus g equal to limit f plus limit g, limit f minus g equal to limit f minus limit g, limit f times g equal to limit f times limit g, limit f by g equal to limit f by limit g provided limit g not equal to 0. The continuity of function of two variables. The continuity of a real valued function of two real variables at a point is defined in terms of limit of the function at that point. Definition. A function f of x y is said to be continuous at a point a b of its domain of definition if limit x y tends to a b f of x y equal to f of a b. The definition of continuity of f of x y at a point a b requires that f must be defined at a b and in certain neighborhood of a b. A function which is not continuous at a point is said to be discontinuous. The discontinuity at a point a b may occur if either limit of the function does not exist or limit exists but different from f of a b. Example, check the continuity at 2, 3 of a real valued function f defined by f of x y equal to 3xy if x y not equal to 2, 3, equal to 6 if x y equal to 2, 3. Here limit x y tends to 2, 3 f of x y equal to limit x y tends to 2, 3, 3 x y equal to 18, but f of 2, 3 equal to 6. Thus limit x y tends to 2, 3 f of x y not equal to f of 2, 3. Therefore, the given function is not continuous at 2, 3. Example, let f be a real valued function of two real variables defined by f of x y equal to x square y by x raised to 4 plus y square if x y not equal to 0, 0, 0 if x y equal to 0, 0. Examine the continuity at 0, 0. Let us consider a straight line path y equal to x through 0, 0. Then f of x y equal to x cube by x raised to 4 plus x square equal to x by x square plus 1 and limit x y tends to 0, 0 f of x y equal to 0. Now consider the parabolic path y equal to x square. In this case, f of x y equal to x raised to 4 by x raised to 4 plus x raised to 4 equal to 1 by 2 and hence limit x y tends to 0, 0 f of x y equal to 1 by 2. The limits of function along two different paths are different. Therefore, the limit does not exist at 0, 0 and hence given function is not continuous. Remark. If a function of two variables is continuous at a point, then it is continuous at that point when considered as a function of single variable. That is, if f of x y is continuous at a b, then f of x b is continuous as a function of x at x equal to a, and the function f of a y is continuous at y equal to b. That is, limit x tends to a f of x b equal to f of a b and limit y tends to b f of a y equal to f of a b. But the converse need not be true. Consider the function defined by f of x y equal to 2xy by x square plus y square if x y not equal to 0, 0, 0 if x y equal to 0, 0. Limit x tends to 0 f of x 0 equal to 0 equal to f of 0, 0 and limit y tends to 0 f of 0 y equal to 0 equal to f of 0, 0. Therefore, the function f of x y is continuous at 0, 0 when considered as a function of single variable. Now, we check the continuity at 0, 0 as a two variable function. Along approach path y equal to x, limit x y tends to 0, 0 f of x y equal to limit x y tends to 0, 0 of 2x square by x square plus x square equal to 1. Along the approach path y equal to x square, limit x y tends to 0, 0 f of x y equal to limit x y tends to 0, 0 2x cube by x square plus x raised to 4, which is equal to limit x y tends to 0, 0 2x by 1 plus x square equal to 0. Therefore, the limit x y tends to 0, 0 f of x y does not exist and the function is not continuous at 0, 0. Algebra of continuous functions. The following results are presented without proof. If f of xy and g of xy are real valued continuous functions at a point a b of the domain f and g, then 1. F plus g, f minus g, f dot g and f by g, where g of ab not equal to 0, are also continuous at ab. The conclusion of these results can be used to prove the continuity of polynomials and rational functions. In this session, we have discussed the existence and non-existence of limit of function of two variables and checked the continuity. Before we conclude, please try to answer the following questions. Evaluate limit xy tends to 1 1 xy minus y minus 2x plus 2 by x minus 1. Check whether the function f of xy equal to x raised to 4 minus y square by x raised to 4 plus y square has limit at 0 0. Using epsilon delta definition, prove that the function f is continuous at 0 0 where f of xy equal to x square plus y square sine 1 by x square plus y square if xy not equal to 0 0, 0 if xy equal to 0 0. Find the value of L such that the function f of xy equal to 3xy by root of x square plus y square if xy not equal to 0 0 equal to L if xy equal to 0 0 is continuous at 0 0. S.C. Malik and Savita Arora, Mathematical Analysis, 4th edition, New Age International Publishers. George B. Thomas, J.R. and Rose L. Fenney, Calculus and Analytic Geometry, 9th edition, Addison Wesley. Hope you enjoyed the session. See you next time. Till then, goodbye. Take care.